All right, what we want to talk about is we want to talk about gases. In order to really talk about gases, we have to real quickly go over what separates our different phases. First, we have solids. And in solids, we have molecules that are locked into place. Molecules or atoms that are really locked into place inside the structure of the solid. And they don't have a great degree of movement. Relative to each other, that is. Because they have so little movement, solids are said to have a fixed shape and a fixed volume. If I was to draw it via one of our little dot structures, we'd say that our molecules are all very close together and very orderly. A liquid, on the other hand, our molecules are close together, but they're in a sort of chaotic random pattern. They have a much higher degree of movement. They have a higher degree of movement, but they really still have to stay close to each other. And we say that a liquid has a variable shape because of that high degree of movement. But because the molecules in a liquid have to stay close to each other, we still refer to a liquid as having a fixed volume. For example, a gallon of milk is a gallon of milk whether it's in the gallon container or whether it's spilled all over your floor. The volume hasn't really changed. Gas molecules, however, have a big difference. Gas molecules don't have to stay close to each other, and they have a high degree of movement. Why don't they have to stay close to each other in a gas when they have to stay close to each other in a solid or a liquid? The big difference boils down to intermolecular forces. Intermolecular forces are the force of attraction between molecules. We know that water, for example, consists of a bunch of little molecules of 2 hydrogen atoms connected to 1 oxygen atom. Why do those little molecules in your glass of water stay together? Why don't they go flying all over the place? Why in ice do those molecules of water stay together in a locked, rigid pattern? The answer is intermolecular forces. There is a force of attraction between these water molecules. We'll go into great detail on force of attractions in another chapter next semester. However, these intermolecular forces are present between molecules in a solid and a liquid. However, they're totally missing in a gas. There is no force of attraction between gas molecules. Therefore, they don't have to stay close to each other, which means that gases can have both variable volume and variable shape. The theory that describes how molecules of a gas act is known as the kinetic molecular theory. The kinetic molecular theory is always different, quite frankly, depending on what book you look at. Most books actually divide it into 4 postulates. Your textbook goes into 5. First, the kinetic molecular theory of gas says that gas consists of tiny particles and that these tiny particles, either atoms or molecules, move about at random. In other words, they're not all moving the same direction as a general rule. Some are going one way, some are going one way, some are going another way, some are going angles, right? So we have a bunch of gas molecules all moving around at random. Second, the volume of the particles themselves is negligible compared to the volume of the gas. Most of the gas container is empty space. This is a really important concept, and it can be one that's kind of hard to grasp. Basically, when we talk about the volume of a gas, we're not talking about the volume of the gas molecules, but the volume that the gas occupies. In other words, if I have a container here, and I have a gas trapped inside it, I'm talking, and I talk about the volume of the gas, I'm really talking about the volume of the container, right? I'm not talking about the volume of the molecules themselves. The analogy I like to use is if I was going to, it would be like describing your volume based on your apartment's size instead of your pants size, right? When we talk about the volume of a gas, we talk about the volume of the gas's apartment as opposed to the volume of the gas's pants. The volume of this container is huge. The volume of the actual gas particles is so small compared to this volume of the container that they occupy that we don't actually consider the volume of the particles themselves when we talk about the volume of a gas. We only talk about the volume of the container that they occupy. Three, the gas particles act independently of one another, and there is no attractive or repulsive force between particles. This is a big one, and as you can imagine, this is something that we can actually create conditions in the lab where this becomes an issue. And we can with the second one as well. But at the moment, this is important. There is no force of attraction for the gas molecules. Gas molecules are the ultimate antisocial particle. In other words, if two gas molecules pass really close to each other, they're not going to be attracted to each other or repulsed. In other words, their trajectory will remain unchanged by passing in proximity to each other. Not only will their trajectory remain unchanged, but their energy will remain unchanged. Because there's no attractive force for them to overcome, they're not going to slow down or lose any energy when they pass by each other. 4. Collisions of gas particles in a container or with the walls of the container are elastic. Elastic is how physics describes any collision in which velocity is conserved, or energy. In other words, if my little particle here strikes the wall of a container with a velocity of v, it will bounce off the wall with a velocity of v. Now, the direction will change, obviously, but the magnitude of that velocity is going to stay the same. Your conditions are elastic. I like to think of it as saying that gas particles behave like Elmer J. Fudd's bullets. Right, we've all seen the Bugs Bunny cartoon. Elmer J. Fudd shoots his gun, boom. What happens? The bullets ricochet endlessly, right? They never slow down, they never stop. They just bounce around forever. That's how gas molecules are. They hit something, they just change direction and keep on going without slowing down. Finally, and one we're going to concentrate a great deal on here in a second, is that the average kinetic energy of gas particles is proportional to the Kelvin temperature of the sample. Translation: if you increase the temperature of a gas, the kinetic energy of the gas particles increases. Kinetic energy, remember, is 1/2 the mass times the velocity squared. Can we change the mass of a particle? No, we can't. So if we increase temperature, we can't increase mass. Instead, we must be increasing velocity. So temperature is directly related to kinetic energy, and it's directly related to velocity. And we'll actually do the math on that here in a second. But that's your kinetic molecular theory. You need to not only know these points, and I'm not going to say, what's the first part of the kinetic molecular theory? No, I'm not going to say that. I'm just going to want you to know what it says, right? Not the associated numbers. I just want you to know the words and the meanings and be able to apply those meanings. All right, let's keep going. All right, just to reiterate, the volume of gas particles are insignificant compared to the volume of the gas they occupied. When we talk about the volume of a gas, we are talking about the gas that the volume occupies, not the volume of the little actual particles. The volume of a gas is actually much, much larger compared to the volume of the particles, and that's what we're talking about. Again, to reiterate, collisions among the gas particles are elastic, meaning they just change velocity, they don't lose energy, and they don't lose velocity. Here's something you want to slow down and focus a little bit more on. Temperature is directly related to the average kinetic energy of a group of molecules. As temperature increases, the average kinetic energy increases. Let's take a look at this graph here. I put it on here for a very good reason. We see three curves. Each of these bell curves, or each of these distribution curves, I shouldn't really call them bell curves, each of these distribution curves is taken at a different temperature. On this axis, you have the percent of the molecules with a given speed, and the speed is on this axis. So at a low temperature, our molecules are moving very slowly. Not only are our molecules moving very slowly, but notice our distribution. Most of our molecules are moving very close to that average speed. As we increase temperature, going from 200 Kelvin to 600 Kelvin and then to 1,000, our average speed increases, right? The average speed being the little tip of our hump, increases, but the distribution also increases. As temperature increases, the average increases, but so does the distribution. The fact that gas particles have an average speed as opposed to a set speed helps us explain why snow sublimates. You've all had the experience of looking outside your window and seeing snow disappear despite the fact that it's below freezing temperature. Where does that snow go? Well, even at the freezing temperature, not all molecules have the same temperature, and therefore not all molecules have the same energy. Instead, there's a distribution of energies. And even at temperatures below freezing, a very, very small portion of those molecules is going to have enough energy to enter the gas phase from the solid phase. The concept that as temperature increases, distribution increases, and that at all temperatures there is a distribution of speeds and thus energies is going to be an important one as we move forward. And that concludes what we really want to say about the kinetic molecular theory.